Good morning, mathematicians. Happy you could join me again today, if and when you are. Well, I guess. Here we go. What are we doing today? That's always the question. I saw some good stuff on Reddit, so we'll start there. Interesting questions. Good morning, Quality. Hope you're doing well. Hope you proved a lot of theorems this weekend. Oh, good morning, Nerdy Quagsire. I hope you proved a lot of theorems this weekend. Yeah, so we got an interesting post right off the bat here. What does von Neumann, one of the greatest, you get that YouTube push notification and tap it like a reaction time test. Hell yeah. That's what I like to see. That's the energy we need in chat. That's the energy we need in this channel. Hell yeah. We've got also good news. There's a lot of content coming out this week. You have an exam in 43 minutes. Should you keep watching? Absolutely. Absolutely. What's your exam on? What exam is it? I mean, the last 43 minutes before your exam is, if you're cooked, you're cooked. If you're gonna cook, you're gonna cook. I think very little will change. Actually, I mean, I still, when it was me, I would still be like reviewing definitions and theorems and proofs up right until the end, because you never know. You never know. You conjectured something that looked to be true, tried to prove it, and then found a counterexample. Welcome to being a mathematician. There's some folklore story about a guy who was, if you Google it, you can probably find it. He was trying to prove something about 7 spheres, and or it was something about spheres, and I think 7 was actually the number of years he like tried to prove that the theorem was true, and then like one day he sat down to see if he could prove it was false, and he was done by the end of the day, which is hilarious. Although of course, so it's funny. It's like, oh, bro wasted like 7 years trying to prove something that was false, but of course, the reason he was able to come up with a proof in a day is because he spent 7 years trying to prove it was true, right? He understood the problem so well from the other side. Yeah, if the exam was on local language, actually, you might be kind of, I don't know if I'd be the best to even prep you for local language. I mean, that's what I do. That's the exam, the area I'm in, but, I'm also in this, like, particular little bubble of geometry. And there's a bunch of stuff that it could be. If it was an exam generally on local language, I don't know. Like, I'd have to read up a bit on that before I took it. Like, I totally blackboxed the theory of supercuspidal representations. It's something I'd like to learn about more one day. Maybe we'll get into it. But discrete math, yeah, super hard stuff. Well, let these words of von Neumann inspire you going into your exam. Yeah, what does von Neumann mean here about the dangers of mathematics becoming too aestheticizing? Oh, I can't speak. Wow, I want to read this whole article, actually. Can I explain what Chern classes are? Yeah. I'll do that in just a moment. But I just want to see what von Neumann's saying here. As mathematical discipline travels far from its empirical source, or still more, von Neumann, by the way, one of the uberest chads of all of math. Or still more, if it is a second and third generation only indirectly inspired from ideas coming from reality, it is beset with very grave dangers. So he is saying I'll read the rest later because it's maybe not so interesting for you guys to sit here while I read this out. But I think in one hand I appreciate his concern. On the other hand, I'm just in it for the love of the game. Hi, Yaman. Wow, did you just say Neumann is soy? How do I kick people from chat? How do I, where's the kick? Go to channel, report, remove. Yeah, careful. Don't make me hit that remove button. How dare you say it? I mean, okay. If you're saying Neumann is soy because he's maybe too practical, and he's against doing mathematics just for its inherent aesthetic beauty. If that's where you're coming from, like, okay, maybe I won't kick you, but still, like, you better watch your words around here. We got to put some respect on that name, even though we might my timbers are shiver. Good, they better be. Think about this during your exam. Okay, we had an actual math question, so let's talk about some actual math. So I wouldn't say I'm a Chern classes pro, but I definitely used some sort of augmented version of Chern theory in my master's thesis. You're watching the video series on SL2Z, and you understand that the function satisfies the group axioms for complex numbers, but is it the only one? If so, why? Trying to understand where this comes from. Oh, well, the hard to imagine that the person who von Neumann hierarchy is named off of would be against abstraction math. Yeah, I mean, yeah, but I think the abstractions von Neumann was interested in. I'm going to read the rest of this article later, but I think they were sort of all rooted in reality, like rooted in questions about reality. So there's like abstract things he was working on, maybe in functional analysis or something, but he had in the back of his mind applications like quantum physics or something. And the von Neumann hierarchy, I mean, you could it's not so I guess there's higher levels of abstraction, right? It's like you could see it as a practical pursuit to like put these considerations on a certain kind of firm foundation. But so geometry of SL2Z, I'll just quickly mention that the thing there is that it's it's not that the function satisfies the axioms, the group axioms, but rather what it is that we have the group, right, SL2Z, and we have the what should I say? How should I say it? I mean, in general, like, this is a group acting on the upper half plane, right? So in general, any group action, right? It is a function. It is a function from G cross X to X. And so that means for each given, if you take some particular given G in G and you plug that into the first component, then sigma with G affixed to G in the first component is a function from X to X that satisfies basically that the composition, like the definition of a group action basically tells you that the composition of these two functions is compatible with the group action, right? So yeah, I mean, I guess you could look at it as like being a collection of functions which satisfy some group law. But if you're looking for like I guess the short answer to your question is no. It's not the only one. There's many group actions. I mean, um, given any group and any set, you can always define at least one action map of that group on that set. Higher levels of abstraction than set theory? Not really. Oh yes. Oh yes. Oh yes, certainly. Certainly. And 100% there's higher levels of abstraction than set theory. And also, I mean, within set theory, there are things that are more or less abstract. And I would say, in the grand scheme of things, the von Neumann hierarchy is pretty down to earth. And in fact, yeah, I would say it's pretty down to earth in the grand scheme of crazy abstractions that could be studied in set theory. So yeah, the rabbit hole goes much deeper. It really does. Yeah. Okay, so let's talk about Chern classes. Chern classes. So what are these? There's various approaches to Chern classes. So there's sort of two main approaches that axioms. Oh yeah, unlike you, nerdy Quagsire, the homotopy type theory master. We all moved on to univalent foundations, gang. Yeah, maybe we should. But so there's the axiomatic approach where basically one first defines a theory of Chern classes for line bundles, and then uses that to get to arbitrary vector bundles, just sort of stipulating some axioms that it plays well with direct sums and stuff. But then there's also so I guess that'd be the synthetic approach, and then there's maybe like the analytic approach, which gives you a sort of explicit way of constructing Chern classes. And this is the analytic approach is the one that I'm more familiar with. So what is a Chern class, though? Well, the fact that there's a class should maybe make you think equivalence class. And what a Chern class is it's a specific cohomology class. So it lives. You've got some manifold. You've got algebraic topology midterm in an hour. Well, good luck to you, Dimma. Definitely good luck to you. We're talking about some algebraic topology right now, so hopefully this will get you amped up and inspired. Oh, I guess it doesn't have to have z coefficients, but sometimes we take normalization, so it does. I'm a little fuzzy on those details now, but yeah, I guess it's exam season. I guess exam season's popping off for people, so good luck to everyone. Yeah, what are Chern classes? They're specific cohomology classes, and we have different ones. There's like the 0th Chern class, the 1st Chern class, ... And so, yeah, as you might imagine, like this is in the first cohomology group. Is there one in the 0? I mean, normally our spaces are connected, so probably there's nothing interesting there. C2 will be in this, and so on and so forth. And then we also have a total Chern character, which is it the sum of them, or I have some vague recollection in my mind that maybe we normalize them like this, maybe not. I don't quite remember. But there's some sort of like total Chern character which encodes all of these. So that's the basic idea of Chern classes. And you might say, okay, well, what does that mean? I mean, there's a bunch of things in cohomology, but it could be useful to have sort of like, it's one thing to know what the cohomology is of your space, like abstractly what the group is isomorphic to, but it could also be really nice to have like explicit generators and relations, because the cohomology means things about certain pieces of your space. Or, for example, something we're going to dive into in a second, we were talking not too long ago about de Rham cohomology of a space, and how somehow de Rham cohomology is like measuring things about the solvability of differential equations on your manifold, right? So it might be useful to have like, okay, I know that my H2 of my space is isomorphic to C2 or something. Okay, but it would be nicer to have explicit information of like, well, what are the and remember, cohomology is it's a quotient, right? It's a quotient. It's a kernel of some map, quotient some image. So we might want to have, in order to do computations, it'd be nice to maybe first off know what the image is, know what things are lying in that image, and also have a nice set of representatives, say, for the equivalence classes. I mean, no different than in modular arithmetic. We tend, you could work with any number you want for all the equivalence classes, but there tend to be ones that are more amenable to computation and help us understand what's really going on. So let me talk about the total Chern character. So, one thing that we want is we have some manifold, like real or complex or something, and we have on that manifold a notion of exterior derivative. So, sort of the first thing you write down is it goes from functions to one forms, but in general, it'll take you from n forms on your manifold to n plus 1 forms. You remember starting from theorems in algebraic number theory, complex analysis, and topology, and reaching the Atiyah-Singer index theorem by clicking on links to generalization on Wikipedia. Yeah. There's certainly, I mean, the Atiyah-Singer index theorem is all wrapped up in this. Like, definitely you need Chern classes for sure that pop up in there. Yeah, that theorem talked about Chern classes. Absolutely. Yeah. So Chern classes are a big part of that, and the Atiyah-Singer index theorem, and I guess more generally, I think the Grothendieck-Riemann-Roch theorem, I think, is even more general, encompasses that as well. And Chern classes also make an appearance there. So there, the Chern classes are actually interpreted as a map going from the cohomology of your space into the K ring. Or is it possibly the other way around? Yeah, I'm rusty on those details. Hello, Matt Miller. So, it definitely makes an appearance like that. One way to get the total Chern character, this is the way I'm familiar with. So we have our exterior derivative on a manifold, right? Gives us some way of differentiating functions, or n forms more generally. And so we might want to extend this a little bit. So given a vector bundle, say E over X, a connection, well, usually we just frame it, again, we start off by framing the connection in the same way. We just frame it as going from like functions in one forms, but it's like how should I write this? It's like sections. It's like sections of the of your manifold valued in the vector bundle. So it basically looks like things like smooth functions tensored with sections of the vector bundle. Up to now it's one forms tensored with sections in your vector bundle. So it allows for some sort of differentiation on the vector bundle. And so it's some sort of, I guess, linear operator on these things. And in order to explicate it as being some sort of differentiation, we ask that it satisfies a Leibniz rule. So you're going to do an exterior derivative in the first component, and then in the second component you'll have f. And I don't really like the way we write it. Like most people write it like as like nabla s, which sort of seems a little self-referential to me. I don't know. I've never really liked writing it that way. But okay, it's the convention. So the nabla here is being interpreted as acting on these tensors, and then the nabla here is just basically some linear transformation in the sections of your vector bundle. There's one other thing we want it to satisfy. I don't remember. There's like two defining conditions, but this is the important one, right? Like, if you want to think of this as a derivative, well, how do you make it think of it as a derivative? Well, you say it has to satisfy some sort of Leibniz rule. That's what gives it derivative vibes. So this is called the connection. Well, I mean, it's just the fact that, like, usually it's not really self-referential, like, because of the way I just explained it there, but the way the notation is like, oh, you're defining what nabla does on pairs, and then somehow it's appeared on like the left and right side of the equation, you know. Isn't it subjective what is more or less abstract? Sure, yeah. Definitely, yeah, subjective, you know, like basic calculus is not abstract to me, but to a bunch of people who are, you know, or I'm invigilating a linear algebra exam today. You know, whatever's on their exam is like baby stuff to me now, and you know, but it's probably like hopelessly abstract for some of the people. So yeah, it's absolutely relative, but you did make a claim about set theory being higher levels of abstraction than set theory. Not really, right? So you made a claim whether there's higher levels or not, and I think even in your subjective experience, I think you'll find there's quite deeper rabbit holes to explore than just set theory. And like I said, set theory itself, I think you'll find even within it, there's layers, like an onion, like an ogre. So it turns out, just like we originally define it down here, and just like how we extend the exterior derivative, we can also extend the connection, so that it takes you from, you know, sections in one forms to sections in n forms to sections in n+1 forms. And there's a difference though, because the exterior derivative has the property that if you apply it twice, then it's just trivial. But it turns out that actually, if you apply the connection twice, you get something which is called the curvature operator. So curvature operator. There are things like infinity categories and higher order logic, but nothing significantly more abstract than arbitrary sets in the von Neumann hierarchy that you know of. Yeah, if that's, I don't know, if you've sat down and studied infinity categories and that was your takeaway, that was somehow much easier to digest than the von Neumann hierarchy. Or have you read the homotopy type theory book? I mean, I guess I gotta take you at your word if you read that book and you found that it was about as difficult for you as the von Neumann hierarchy. But I would be very surprised if that was the truth. But I guess I'll just have to take you at your word. Hello, I'm taking linear algebra at the moment. Can I ask you why the determinant is defined the way it is? It feels dry and unmotivating learning it that way. That's a fair question. Yeah, I mean, I think the way we normally encounter the determinant is, it's sort of post hoc justification, right? You later find out it's a tool for determining whether matrices are invertible or not. Thank you. You're the first person to comment on the painting and the plants. That was a painting a very talented friend of mine made a while ago, and it took her like 30 minutes. She painted it with her hands. Incredible. Yeah, and not all my plants are on display, but I started tilting the computer so you can see the plants and the tops of some of my guitars in the background. That's all of my guitars. What am I talking about? So yeah, so okay, I can give you one other definition for the determinant that is basis free, and you might I don't know if you'll find this as motivating though. Like, I don't know if you'll find this any more or less dry. Because yeah, I think it's just the value of the determinant does come over time. As you see it used more and more in more situations. So yeah, unfortunately, it might just be one of those things that comes with mathematical experience. There are abstract, easy things and complicated real life problems. That's true. Yeah, I know abstract. Yeah, not the same as difficult, but. I mean, yeah, in my mind, I think, well, actually, I mean, maybe types in homotopy type theory are easy to visualize because it's geometrically motivated. But, yeah, I'll have to think about that. But yeah, let me, actually, and this has some, so I'll put a pause on the curvature stuff for a second, to talk about the determinant. So, actually, this is very related to everything we're talking about because it has connections to differential forms and stuff. So, suppose you have a linear transformation on some vector space. Whoa, didn't mean for that to happen. You've got a linear transformation on some vector space, and so there's a couple different operations we can do on vector spaces. So you may or may not have heard of, say, the direct sum of two vector spaces, right? You just put them together. Maybe also have heard of tensor products. I have a series on tensor products you can go watch. The old videos are lower. Actually, they're not so bad. One of these days, hopefully soon, I'll get around to finishing this series. But there's some important subspaces of the tensor product that we pull out of here, and one of them is the wedge space of two vector spaces. So this is not a precise formal definition, but let's suppose you had a basis V1 through Vn, and another basis W1 through Wm, then your wedge space is going to be the span of these symbols, say Vi wedge. Actually, I should do it. Sorry. I'm going to do this. I'm going to do this with VV. So forget the second basis here. So it's going to be the span of Vi, Vj, such that, I guess which way do we want it? J is strictly bigger than I. So you do have symbols. You are allowed to write something like V2 wedge V1 if you want, but in this space, it turns out that if you have the wedge of two vectors, that's the negative of switching their components. So in particular, V1 has to be 0, because if you had both ones here, you would have this has to be equal to its negative, so it better be the 0 vector. Right, okay, if this is in the definition of differential forms that we talked about up here. I mean, the differential forms is basically like the n forms are a bunch of it's just n wedges of the space of one forms. So this also tells us, and you can keep wedging, by the way, right? So you could do the triple wedge of a vector space, and now this will be the span of Vi wedge Vj wedge Vk, and again you could take it so that I is less than j is less than k, because again you'll have the operation, and I should say this relation doesn't just apply to any vector. Also, if you have like UVW, if you swap any two, you pick up a minus sign. You can determine the determinant by saying it's a non-degenerate alternating multilinear form. Yes, this is exactly where we're going. That's exactly where we're going, yeah. Maybe one more property is there. Yeah, this is the way you defined it in your lecture, then got the formula. Yeah, this is actually what I'm working towards here is pretty much an equivalent way to say it. Exactly. Yeah. So now, so we've talked about the linear transformation. We have these wedge spaces. You also get a map. So if you have a linear transformation, say from V to V, then you get an induced map on any of the wedge spaces. So, for example, we can define a map T2 on wedge 2V to wedge 2V. And how do we define that map? Well, you might just sort of try the obvious thing, right? So how are you going to define it on some wedge UV? Well, you define it to be TU wedge TV. And there you go. And I guess one of the other relations I didn't tell you about is that alpha U, if alpha is a scalar, alpha U wedged with V is equal to alpha times U wedge V is equal to U wedge alpha V. So that's the other important relation here. So it's bilinear. Also additivity in both components, but okay. So this gives you a linear transformation between the wedge spaces. And so if V is n-dimensional, well, then that means, by what I told you before, the nth wedge space, this is just going to be the span of V1 wedge, V2 wedge, ... up to Vn, right? It's going to be a one-dimensional space because there's n wedges, so there needs to be n vectors there, and we can't have two of any vector because that would make it 0 because of our negativity swapping relation. So what that means is However, so Tn, the induced linear transformation on the nth wedge, well, what is that going to do to this vector? Tn applied to this vector, again, this is a one-dimensional vector space, so all you can do is scale things. So that's just going to scale it by some number alpha. And guess what? Alpha is the determinant of the original linear transformation T expressed as a matrix in terms of this basis V1 to Vn. So, I don't know. Maybe that made it worse. Maybe that made it less motivating or something. But I think this is an interesting perspective on the determinant. And yeah, this is exactly equivalent to what Tibet said in chat. Yeah, so worth checking out, I think. Yeah. Okay, so let's go back. We had a fun little digression there. Let's go back to this curvature operator and talk about Chern classes. So this curvature operator can basically be viewed as a matrix. You can basically view this as a matrix valued in two forms. So what I mean by that is basically like when you apply your curvature operator to some thing like this. So here you've got some smooth function, and this is some section of your vector bundle. It basically works out to like multiplying this. You can interpret theta as just some matrix of two forms, basically. So, yeah. Spoilers, also probably wrong, noting that worth noting that the wedge product corresponds to volumes in a nice geometric way. Yes, exactly. And that's exactly why the wedge product is used in the definition of differential forms, because differential forms are basically things that want to be integrated, and those exist so that we have a theory of integration on manifolds. And yeah, the wedge product, you're right, totally corresponds to volumes, and that's why they show up. It's all connected, man. So remember also that your manifold only has the largest the differential forms are all going to be 0 when n is larger than the dimension of your manifold, right? So your top forms are just your degree n forms, for the exact same reason of what I just said, by the way, for wedge spaces of vector spaces, right? Because this is basically just n wedges of your cotangent bundle. So what this means is we can actually define the exponential, even though this is normally a transcendental function, the exponential, maybe I should write it in terms of theta here, by just borrowing the power series expansion, right? So this will just be the identity plus theta plus theta squared over 2 factorial plus theta 3 over 3 factorial, and so on and so forth. And the thing is, because eventually, so this will be 2 forms, this will be 4 forms, this will be 6 forms, and so on. And eventually, we know that theta has to die, because eventually you'll get to forms that are above the dimension of your manifold. So this actually is, even though we read it as like this exponential, this actually is a finite sum. And it turns out that your total Chern character, so remember I said that we have this, if we sum all of our Chern classes together, this is the total Chern character. This can be defined to be the, oh God, am I going to say the wrong thing? So I believe it's the trace of e to the theta. And in particular, so the trace, right, this is going to be a sum of differential forms, alpha 1, alpha 2. So this is, say, degree 1, degree 2, maybe we have a degree 0, 1, all the way up to degree n. And these should correspond to each of the individual Chern characters in each degree. And so this is really nice because this actually gives us like an explicit way to, we actually have like explicit representatives for these cohomology classes in de Rham cohomology. So maybe I can just show you some examples to leave us off with. So computations, I'll go right to the end here. So here's a particular case of a manifold. Well, here I'm using some tricks because I haven't touched on like the holomorphic case specifically yet. Like there's nice things that happen there. Maybe I'll say that in the future, but I'm just about done my coffee, so time to go and prove some theorems. But right, so here is we can always locally describe our connection as the exterior derivative plus some sort of matrix of 1 forms, little theta. And so here I do an explicit computation of that. Well, in this case, it's a 1-by-1 matrix, right? So I just have this 1 form here. And then I do a computation of the 2 form, as you can see here, big theta, that corresponds to it. And let's see, where do I have? Right, so then, okay, it's not so obvious the way I've written things here, but basically what I'm doing is I'm computing theta on different basis elements in order to get a matrix. And so you see here I'm performing a trace of some matrix. It turns out to have like a really simple form in this case. Okay, technically in this document there's more complicated things going on. It's a holomorphic vector bundle to some sort of like super trace or whatever. What advice would I give to someone who is new into topology, low-dimensional topology, just finished Milnor and Stasheff characteristic classes? Well, I don't know what advice to give you because you probably know more about characteristic classes than me, to be honest. So I should be asking for you advice. I should be asking you for advice on what to read about next. If you've already read, isn't that a big book? That's a big book. I could be misremembering, but yeah, sorry, I don't know what to say. You probably know more low-dimensional topology than I do. Yeah. Here's another example. Here's a more realistic example where I have some big matrix and same thing. Basically, just computing the exponential of that and taking some sort of trace. So. Anyways, I think that'll do it for today. So thanks everyone for joining me, and go prove some theorems.